Source code repositories sit at the center of modern software delivery, and that makes them unusually attractive targets. If an attacker can influence what developers build, test, and deploy, they do not need to break into every production system one by one, because the organization will distribute the attacker's changes for them. That is why repository security is not just an internal developer concern, but a core part of enterprise security posture. When you treat repositories as high-value assets, you start asking different questions about identity, privilege, integrity, and recovery than you would for an ordinary file share. The payoff is that you reduce the odds of a quiet compromise that turns into a wide-scale supply chain incident.
At the foundation, repository permissions define who can read code, who can propose changes, who can approve changes, and who can administer the system itself. Read access matters because code contains design details, security assumptions, and sometimes data handling logic that can guide an attacker toward the weakest seams. Write access matters because it determines who can introduce changes that later become trusted artifacts, even if the change looks harmless at a glance. Administrative access matters most because it can override controls, change policies, and manipulate audit evidence, which means it deserves the strictest scrutiny. A strong permission model makes these distinctions explicit and avoids the trap of giving broad access for convenience that later becomes the root cause of a compromise.
Branch protections exist to keep the most important lines of code from being changed casually or invisibly. The simplest idea is that you do not want direct, unreviewed pushes to the branch that represents what the organization builds and releases. By requiring changes to flow through controlled merge processes, you gain checkpoints where policy can be enforced and where identity and intent can be evaluated. These protections also reduce the impact of a compromised developer workstation because the attacker cannot immediately rewrite critical code and ship it before anyone notices. When configured well, branch protections create a predictable pathway for change that is easier to monitor, easier to audit, and harder to bypass without leaving evidence. Code review requirements add a human control that complements automated checks because experienced reviewers can spot risks that tools may miss. The goal is not to create bureaucracy, but to ensure that changes affecting security, authentication, authorization, and data handling receive meaningful scrutiny before they become part of the mainline code. Review also improves accountability because changes are no longer a private act but a shared decision that leaves a record of who examined what. This becomes especially important when code changes involve subtle logic that could enable broken access control, weak cryptography, or unsafe input handling. When reviews are treated as an engineering quality practice rather than a compliance ritual, they serve as a practical barrier against both accidental mistakes and deliberate manipulation. Integrity and accountability become stronger when commits are signed because signing ties a code change to a cryptographic identity rather than relying solely on a username field. A signed commit provides higher confidence that the content was created by the claimed author and was not modified after signing without detection.
This matters in investigations where you need to understand whether a suspicious change came from a real developer, a compromised account, or an attacker trying to impersonate someone.
It also matters in environments with multiple tools and mirrors, where changes may move across systems and you need a consistent method to verify authenticity. Signed commits do not eliminate all risk, but they raise the cost of certain attack paths and improve forensic clarity when something goes wrong. Few repository mistakes are as damaging and as common as storing secrets directly in code or configuration tracked by version history. Even if a secret is removed later, the repository history can preserve it indefinitely, and clones, forks, and backups can spread it beyond the original team's control. A key, token, or credential leaked this way can become a durable entry point for attackers because it is often valid long enough to be exploited, especially when rotation practices are weak. The risk is amplified by the fact that repositories are designed to replicate, which is exactly the opposite behavior you want for sensitive credentials.
Treating secrets as data that must never cross into source control is one of the clearest boundary disciplines in secure development.
Secret scanning is a control designed to catch that discipline failure as early as possible, ideally before a secret becomes widely distributed. Scanners look for patterns associated with keys, tokens, and credentials, and can alert or block changes that appear to introduce sensitive material. The practical advantage is speed, because finding a secret quickly can limit exposure and reduce the number of places where rotation and cleanup must occur. The limitations are also important, because scanning cannot detect every possible secret format, and it can be evaded by encoding, fragmentation, or novel patterns.
That is why secret scanning should be treated as a safety net, not as permission to store secrets in repositories, and it should be paired with clear guidance on secure secret handling.
Dependency files deserve careful governance because they define what third-party code is pulled into your builds, and that code becomes part of your trusted software. When dependency definitions change, the risk is not only functional breakage, but also introduction of vulnerable or malicious components.
Attackers understand this and sometimes target dependency updates because they can be less visible than direct edits to business logic.
Good control here means understanding which files and manifests govern dependencies, ensuring changes to them receive review, and enforcing policies around allowed sources and versions.
The point is to prevent uncontrolled drift in what your software is actually made of, because you cannot manage risk in components you do not deliberately track and approve. Access logging gives you the visibility needed to detect unusual repository behavior and to support investigations when anomalies occur. You want to know when large-scale cloning happens, when permissions are changed, when new tokens are created, and when administrative settings are modified. Logging is not just for after-the-fact reconstruction, because it can also support early detection if you monitor for patterns that do not fit normal team activity. For example, a sudden spike in clone activity from unfamiliar locations or repeated permission escalations can be an early sign of account compromise. The value of logging depends on completeness and retention, because gaps and short retention windows create blind spots that attackers can exploit. Least privilege is particularly important in repositories because administrative capabilities can effectively rewrite the rules of trust. If too many people can administer projects, manage integrations, or bypass protections, then the repository becomes a soft target for supply chain compromise. Limiting administration reduces the chance that a single compromised account can disable branch protections, alter review requirements, or manipulate integrity controls. It also reduces accidental misconfiguration, because fewer people have the power to make high-impact changes without realizing the consequences. Least privilege is not about slowing work down, but about ensuring that power is granted deliberately, reviewed periodically, and aligned with clear responsibilities. Service accounts and automation tokens introduce a distinct risk profile because they often operate continuously and at scale. Automation needs access to repositories to run builds, tests, and deployment steps, but those credentials become valuable targets because they can act without human presence. Scoped permissions are essential here, meaning the token should have only the minimum rights needed for its specific task, and not broad access to every repository and administrative function. Rotation matters because long-lived tokens tend to be forgotten, and forgotten credentials become permanent footholds. When you treat automation identities with the same seriousness as human identities, including monitoring and lifecycle control, you reduce the chance that a pipeline becomes the easiest path into your development ecosystem. Backups are a security control for availability and recovery, and they matter for repositories even when integrity is your primary concern. Repository corruption, accidental deletion, or malicious destruction can halt development and delay incident response, especially if the repository also contains infrastructure templates and deployment definitions. A backup strategy should assume that the repository itself could be the target, which means backups must be protected from the same credentials that can modify or delete the primary data. Recovery procedures matter as much as the existence of backups, because a backup that cannot be restored reliably under pressure is functionally useless. When backups are treated as part of operational resilience, they support both business continuity and faster containment after a compromise. Segregation is a structural control that reduces the chance that exposure in one repository domain spills into another. Open-source projects often have different collaboration patterns, contribution models, and exposure to external users than internal proprietary repositories. If you mix these without clear boundaries, you can accidentally grant external actors visibility into internal code or allow internal automation credentials to interact with less trusted environments. Separation also supports different policy requirements, because what is appropriate for an open-source project may be inappropriate for a system that builds regulated products or handles sensitive data. By keeping these worlds distinct, you reduce complexity in permissions, reduce accidental data leakage, and make monitoring signals easier to interpret. When you take all of these controls together, the central theme is that repositories are not just storage, they are trust engines for the software supply chain. Permissions, branch protections, reviews, signing, secret controls, dependency governance, logging, least privilege, automation hygiene, backups, and segregation all contribute to the same goal, protecting what becomes production reality. If an attacker can change code or its dependencies without detection, they can often bypass many downstream security layers because the organization will faithfully deploy the compromised output. Repository security, therefore, becomes a practical expression of integrity, not as an abstract principle, but as the daily enforcement of who can change what and how those changes are validated. When you defend repositories well, you are defending the organization's ability to trust its own software. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.